In this lecture, we will elaborate more on work. So we'll go beyond just the mechanical work, and we'll address various forms of work that you may encounter in a thermodynamic setting. So it's important to understand that when a system is in a thermodynamic state, you cannot associate a work to that system, okay, to that thermodynamic state. What you can associate is whenever you can associate work, that is often when the system is transforming from one thermodynamic state to another thermodynamic state. Okay, so there are other ways it can transform, by heat, for example. But what I'm trying to emphasize here is work is energy in transit. Okay, so that's when the system is changing, then we can talk about work. Okay, but when the system is in a particular thermodynamic state, we cannot really refer to something as work, okay, associated with that particular state. So in an earlier lecture, what we had done was we had defined some aspect of mechanical work. Okay, so we had used this definition: form of energy that can be converted to mechanical work completely or directly by an ideal mechanical device like ideal turbine. Okay, so this is what we had elaborated, and this is all towards the first law. Okay, so we had in an earlier lecture we had done change in how do you think about internal energy and its change. And in this lecture, we are going to focus on this particular aspect of thermodynamic first law. And in the following lecture, we will do heat, which would give us a more complete idea of what is the first thermodynamic law. So let's get started. So work is something which you're familiar from high school. Okay, so force times displacement and so on. Okay, so if the force is not constant, we can integrate. All these things are fairly elementary notions which you are familiar for a long time. So we are not really referring to reversible and quasi-static transformation. Okay, so this work from mechanics can have some friction in it and so on. So we are not really talking about quasi-static transformation. Okay, so the meaning of reversible transformation and quasi-static transformation becomes important in the context of thermodynamics. For example, you can also consider shaft work within the context of mechanical work. So here there's a shaft which is applying a torque, which is making this object rotate. We can connect the force applied to R and define the torque. So this is often the way ships move. So this is not, this shaft is under the water. So you can connect the distance traveled to number of revolutions undertaken, and then you can connect the shaft work to the distance traveled times the force. So that will give you the shaft work, and also connecting it to the frequency in dot will give you the power. Okay, transmitted through the shaft is the shaft work done per unit time. Okay, so this again, you must be familiar with this in the context of classical mechanics. So we can get to a slightly more complicated situation where we appeal to a material property. What do I mean by material property here? This spring constant is something characteristic of this material. In the previous case, for example, we are only talking about the force and the work. Okay, so there is no material property involved. But here we are appealing to a material property called spring constant. So we have a notion of a solid lattice, which under small displacement. Okay, so that is what we mean by a small displacement is when the restoring force is proportional to in terms of quantitatively proportional to, not to displacement. Okay, so and in some way the material behaves symmetrically against both the distortion. That is, either when it is expanded or compressed, there is a restoring force. Okay, so there is a harmonic potential, and there is a displacement around this potential, right? So all these things you learned it probably in your high school. We refer to as a Hookean spring. Uh, and for small displacement, you can this Hookean behavior of springs is applicable. Okay, so it is a material property, because under many deformation there can be other things like creep and so on, fatigue, and creep might come into play. Okay, under large displacement there can be plastic deformation of the spring. All these can occur, but in the most simplest context, we are not referring to any of this. Okay, so this is the first case where we go on from just a simple mechanical situation to a situation that appeals to the material property. We can also consider this kind of a deformation on an elastic bar. Okay, so again, the deformation is elastic. That is the restoring force. That is, we are considering small deformation under mechanical stress. We can connect it to the area of the bar. The emphasis here is on infinitesimal deformation. Okay, so this is also an infinitesimal deformation. So under these regimes, small deformations done in a slow manner, we can talk about this Hookean type of behavior. So so this would give rise to volume. Okay, A times dx is the dv. Okay, so all these things, there is the block, the shaft, and this elastomechanical work are covered within mechanics. Okay, within classical mechanics, you can see some kind of a deformation. That is, there is a boundary where there is force, and there's a displacement against the force. Okay, so so that's the way you think about it. Okay, so there is a system boundary, there's a force, and there's displacement against the force. Even in the case of a shaft, you can think about a displacement at the system boundary. Okay, so all right, so how this is all within the framework of classical mechanics. So now we increase the complexity of our description in terms of work. So we go to electrical work. Okay, so when we talk about electrical work, there is no obvious displacement to talk about. Okay, so we can still talk about work in terms of the potential difference and amount of charge in terms of, let's say, coulombs, amount of charge that is transferred. Okay, so they are transferred against a potential difference, some amount of charge that is being transferred. This is the way you talk about. We refer to as electrical work. We can you are also used to the notion of electrical power, V times I. And if the potential difference change with time, you can integrate this. Okay, or if the potential difference is held constant, you can use a simpler formula, and you can think about electrical work. Okay, so what is to be noted is there is no obvious way of referring to a displacement against a force at the boundary. Okay, so how do you reconcile these notions, and how do you reconcile this within the framework of thermodynamics? So this was an important question in the early days of thermodynamics. So Planck and Kenan, so they came up with a definition of work done within the context of thermodynamics. So first, let me just read out the definition. Work done by a system on the surrounding during a process is defined as that interaction whose sole effect external to the system could be viewed as the raising of a mass through a distance against gravitational force. Okay, so there are a couple of things we have to be focusing here. Okay, first, there is always two things. There is a system and a surrounding. Okay, either the system does something to the surrounding or a surrounding does something to the system. In both the cases, there is a process. Okay, so wherein a system goes from one state, thermodynamic state, to another thermodynamic state. Okay, and all these effects, okay, this transformation, okay, so can be thought of as raising or lowering of a mass. Okay, so this is the way we are going to contrast this kind of transformation against heat. Okay, so we are going to talk about two things here. I mean, see, when you're talking about first law, there are two terms. Okay, on the right side, on the left side, there is change in internal energy. On the right side, there is work interaction and heat interaction. This entire definition is about work interaction. Okay, so for example, when you're thinking about work done by a battery, okay, on a system, even though there is no explicit raising of a weight, okay, so most of the time this battery is you can consider the current flowing through a resistor. This can be lighting of a bulb and so on. Okay, but you can, the current that is passing through that resistor is equivalent, can be considered in an equivalent manner to the current that is passing through a motor. This motor is used to run a pulley which raises this mass. Okay, so this is the way we can think. Okay, so for example, this is during discharge of a battery, you are raising this mass, that is, you are increasing the potential energy of this mass, and during charging of the battery, this mass can be lowered, therefore this battery can be charged. Okay, so so this whole raising or lowering of a mass it can be considered in all contexts within thermodynamics. Okay, so sometimes it becomes more, there are subtler points as in different contexts, but in some ways this can always be any work, thermodynamic work can be mapped onto this kind of raising or lowering of weight. All right. So even though there is no explicit displacement, okay, for when the current is flowing, we can think about displacement against a force field. Okay, so all right. So this is the way we move on from a mechanical work to thermodynamic work. Okay, so what I'm trying to say is this resistor, in place of this resistor, you can consider a motor which is connected to a pulley and a mass. Okay, so we can move from mechanical work to thermodynamic work with this definition. All right, so then we can think about certain other forces that you often encounter in a thermodynamic setting. For example, here I am referring to surface tension. This is quite subtle. Okay, so we won't have time to elaborate on all these things. That you can go through the Wikipedia link, for example. So, but I'll briefly tell you why there is surface tension. So in the interior of liquid, if you consider a particular atom or a molecule, it is interacting isotropically against many other molecules. Okay, so when this atom is on a surface, there is an essential anisotropy. Okay, so there is molecules here of the condensed medium of the liquid, but there are no molecules here. Okay, so some bonding has been eliminated for these molecules. Okay, so it tries to bond further. Okay, so when there is under coordination, okay, where there is lesser coordination of these molecules on the surface, they would try to form more bonds, increase the bonding interaction with the molecules that are present here. Okay, so this way of thinking about surface tension is very similar to the way we think about surface stress of a solid. Okay, so there is a certain advantage in thinking through, in making an analogy with respect to surface stress. See, I can understand right now that you are equally unaware of surface stress and surface tension. Okay, so to explain surface tension, I am using this the notion of bonding under coordination, and these molecules wanting to enhance bonding along a surface layer. This is the kind of language one uses when explaining surface stress. There is a certain advantages because in terms of quantitative computations, that model has certain advantages. So I'm using that language, but you can understand better surface tension better by going through this link. So there exists certain tension along this particular outermost layer of a liquid. Okay, so when there is when it forms an interface, that is liquid here, there is let's say gas on this side. So there is a surface tension here. Okay, so the take-home message is certain bonds are broken. There is a bonding asymmetry in this layer, and this bonding asymmetry creates a tension. Okay, so there is no compression. Okay, there is only surface tension. Okay, likewise, when you create a solid surface, the surface stress is of a particular nature. Okay, so so there is no surface compression, there is surface tension because of this bonding asymmetry at the surface. So this, you can also do work against this surface tension. So supposing this is a soap film, you can pull this soap film, and while you're pulling that soap film, you're creating no new area. All right. So you can do work against surface tension. And this work can be written in this manner. Okay, so this is force per unit length. This is the new area, infinitesimal area that is created. So the unit here would be work, right? This is force times distance, unit of work, that is the same unit of energy, right? So you can think about surface tension work. So what is important to note is surface tension is a thermodynamic quantity. So it is a function of pressure, volume, pressure, temperature, and what is called chemical potential. That is, if you we have not introduced this term chemical potential, so we are going to use this term in a discursive manner. Okay, just for discussion. That's what I mean by a discursive manner. We will clarify this term at a later stage. Okay, when we talk about chemical equilibria, chemical potential will be clarified at that time. Okay. So right now, what you have to understand that surface tension is dependent upon pressure, temperature, and chemical potential of molecules. For example, if this interface had surfactants, okay, the surface tension can be significantly reduced. So the surface tension is a function of pressure, temperature, and the chemical potentials of molecule that are present in the surface layer. Right? So this is a thermodynamic variable. All right. So you can also think about an electrochemical work. For example, a very important case of battery, and the battery, when battery is discharging, so inside the battery, there is an exothermic reaction that is occurring. Okay, when you're charging a battery, you're using an external source to run an endothermic reaction inside the battery. Okay, so that's the difference between a battery discharging and battery charging in terms of reactions that are occurring within the battery. So an electrolytic cell is again in an electrolytic cell. If you do, let's say, water electrolysis, or it is said that 3% of world energy, world electrical power goes into what is called chloralkali industry. Okay, so to make NaOH and chlorine and so on. That's a very important electrochemical, the largest electrochemical process. So where you supply electrical power to run an endothermic reaction. Okay, that's what you mean by an electrolytic cell. Okay, so this is a power consuming device. All right. So before we go into this in slightly more detail, we have to really understand what is a voltmeter measure. Okay, whenever we say voltmeter measure, we're used to this measurement, like we used to from high school, a thermometer measurement, a barometer measurement, and so on. Okay, in the early part of this course, even we try to look at what exactly you mean by measurement made by a thermometer, right? So likewise here, we'll go a little bit more into what does a voltmeter really measure. Okay, so these are a lot of subtle points. We won't have time to go into all these details because there are other details, like depends upon the metal that you use to make a contact with the electrodes. Okay, so the voltmeter will have a wire. That wire might be the metal might be different from the metal that goes into these electrodes. Okay, that the electrodes can be made up of a different metal and so on. With all these things, the interpretation of the voltage is slightly different. But without going into such complications, I will give a very simplistic view of what a voltmeter measures. Okay, so the voltmeter measures the energy difference between electron reservoirs. Okay, so you are used to this term reservoirs, for example, or like for example, in what context? In your high school, you have heard about thermal reservoirs or thermal baths, right? So what do you mean? So these thermal baths and thermal reservoirs are like ocean and atmosphere. These have infinite heat capacity. Okay, so any amount of heat you add or remove from that reservoir doesn't really change the temperature of the thermal reservoir. Okay, so that's the context of reservoirs in your probably previous experience. So here we are talking about electron reservoirs. So when so this reservoir is able to supply electrons at a particular energy. Okay, so in a small transformation, you are removing, let's say, infinitesimal current. During this infinitesimal charge transfer, the potential, the energy of the electrons coming out of the reservoir is not changing. Okay, so the voltmeter measures between the energy difference between two electron reservoirs. One is called the anode, another is called a cathode. Okay, there's a potential difference, potential energy difference between these 2 points, these two electron reservoirs. And it's important to understand this is not a mechanical variable. Okay, so this is a thermodynamic variable. So you might have in your electricity magnetism class, electrodynamics class, which you have taken from Griffith, you have heard, you've talked about Poisson equation. Okay, so Poisson equation, you talk about electrostatic potential. Okay, so that electrostatic potential there is a mechanical variable. That's not a thermodynamic variable. But here, when we talk about electrochemical potential difference, okay, that's what you measure. The voltmeter measures electrochemical potential difference, not an electrostatic potential difference. Okay, so this electrochemical potential is a thermodynamic variable, depends upon temperature and pressure, and also a chemical potential that we have not explicitly indicated. So you have to be clear about the potentials that you talk in electrostatics and potentials you talk in the context of electrochemical systems. Okay, so here all these things are thermodynamic quantities. All right. All right. So again, you can talk about work here. So that depends upon potential energy difference measured in terms of volts, Or you might also be used to some other term called electromotive force. Okay, so this is again a thermodynamic quantity times the charge transferred, okay, in terms of coulombs. Okay, so you can talk about work in that context. This is all thermodynamic work. And so you're doing all these transformation in a quasi-static manner. We'll again clarify a little bit in a later lecture what you mean by quasi-static transformation here. We can talk about a power in terms of V times I. Okay, so these formulas you're used to from high school. So at this level, you have to go into sort of deeper level. Okay, so what exactly we may mean by all these measurements and these definition in the context of thermodynamics. All right. We can go to, let's say, magnetic work. Okay, so magnetism is even more subtle. Okay, why? For example, you heard about Lorentz force, right? So there's a force on a moving charge. It's very interesting, right? So in the sense that the velocity is perpendicular, the force is perpendicular to the velocity. Okay, so the displacement, which is indicated by this velocity, is always perpendicular to the force. Okay, so magnetic force does no work on a moving charge. So you probably heard about this statement in your high school. So what is the consequence? The speed remains the same, but the direction continuously changes. Okay, so this is a magnetic force on a moving charge. So, however, what is important to, let's say, electrical engineering, motors, and so on, we are thinking about a magnetic torque and a current loop. Okay, so this magnetic torque and current loop, there is a work interaction. Okay, the work interaction is depends upon delta theta. Okay, that is the extent to which the current loop rotates, and times the torque on the current loop. Okay, so see, this is all not a course on interfacial phenomena, not a course on electrochemical science engineering, not a course on power systems. Okay, so we can only throw in these things just to introduce these terms in the context of thermodynamics. Okay, to get a greater understanding, you have to go. The first source is go to wiki pages and then read more. Okay, but for completeness, we have to introduce these terms so that you are aware of these complications. So this is there is work interaction between torque and a current loop. Okay, when it is rotating delta theta by this displacement, there is a work interaction. So a current loop at an atomic level gives rise to this notion of a magnetic moment. Okay, so you can there is something called an electronic orbital angular momentum that can be considered like a current loop that gives rise to a magnetic moment. And even without this current loop, there is an entirely quantum mechanical phenomenon called spin angular momentum. Okay, so this orbital angular momentum, there's a classical counterpart. There's a macroscopic current loop, and there's a microscopic current loop at an atomic level. That's what you mean by a magnetic moment. So, but when you go to spin angular momentum, there is no classical counterpart, and this is very important. Okay, this with this. If you ask the question of why certain materials are magnetic and certain other materials are not magnetic, we have to take into account both these kinds of magnetic moments. Okay, all these things are associated with certain angular momenta, right? So when this angular momentum, okay, when these magnetic moments are associated with this angular momentum, when these magnetic moments are changed due to an external magnetic field in a paramagnetic material, we talk about work interaction. Okay, so you can to change angular momentum, you again magnetic momenta, we can think about a magnetic torque, okay, and a current loop. Okay, so in analogy with this, okay, we can think about how an external magnetic field changes the magnetic moment in a paramagnetic substance. There are a lot of subtle points. It gets quite complicated, but these are being addressed in the literature. A lot of more detailed, slightly advanced thermodynamic books talk about these kinds of issues. If you're interested, you can go through that. We can talk about it later in one of the discussion hour. So you can, there are explicit formula available here. The work interaction depends upon, this is a constant, this is the permeability of free space, often referred to as mu naught in terms of free space, mu in terms of some other systems, but it's a constant, okay? This is magnetic field strength, and the change, differential change in magnetic dipole moment. Okay, so there is, you can polarize this medium, you can change the dipole moment a little bit, and you can associate magnetic work associated with these. Okay, there's a lot of implications for these kinds of things associated with Nobel Prize work. But you can go, you may go into this in an advanced class, but magnetic work also exists. And there's also magnetic medium has magnetic moments, whereas a dielectric medium has a dielectric. Dielectric is just positive and negative charge, the dipole moment, right? So here there's a magnetic moment in a magnetic field. There's a dipole moment in a dielectric medium, okay? So again, this is the polarization. This polarization in a volume element can be changed in an infinitesimal manner. So this is an infinitesimal change in polarization in a dielectric medium in an external electric field. Okay, so this is associated with a dielectric work. Okay, so this can also be done. Okay, so all these kind of work which can be represented within the thermodynamic framework do exist, have very important applications. Okay, so in real day-to-day life, in practical applications like capacitors, diamagnetic cooling, okay, all these things have to be dealt with, but this is an introductory class, so we are just going to introduce these notions without elaborating in great detail. But if you're interested, there are references, advanced thermodynamic books, which go into this in greater detail. But at least you should be aware that this framework, okay, thermodynamic framework, is fairly all-encompassing. Okay, it takes into account all these kinds of interactions and can be represented in a thermodynamic framework, within the thermodynamic framework. So in general, as a concluding slide, all these kinds of interaction, okay, where did we start? We started with the simplistic system, right? The simplest system is PV work, right? So PdV can be broken down into dx times area of the piston, right? P times dx is the force. P times A is the force. This force is undergoing a displacement dx, right? So that gave rise to PV work, right? So that's where we started, okay? So that is easy to understand. Then we went to some interfacial phenomena, surface tension forces. We went to electrochemical work, magnetic work, work in a dielectric medium, okay? So all these things have a certain feature associated, okay? So all these things that are indicated in the red, okay, can be considered as a generalized force, okay? These are all intensive quantities, and all these things are extensive quantities. These are called generalized displacement. Okay, so the product of generalized force times generalized displacement has a unit of work and energy. Okay, the work, heat are all energy in transit, therefore they have the unit of energy. Okay, so all these things can be considered in a unified framework within the context of thermodynamics. this book, okay, Moran and Shapiro, okay, goes into this little bit, a little bit more. So this again, this book, all these books are undergraduate equivalent books, okay, that could have been used. We are using Schengel and Boles for certain reasons. We could have used any of these books. All these have great explanation. So these are all referenced in the first course handout. My hope is you take a look at these things, okay, when something is not clear. For example, this notion of generalized force and generalized displacement is there in Moran and Shapiro's book. You can go to refer to that, at least that section. That's the whole point of giving you a set of reference books. You should, in the hope that you go and read them, all right? All right, there's one additional point I would want to emphasize. All these things are reversible transformation, okay? This, we can talk about this for an hour, okay? But we are going to just touch upon three aspects of reversible transformation, okay? So how do you implement reversible transformation within the context of thermodynamics, okay? So reversible transformation, again, this has to do with this notion of quasi-static transformation, okay? First, these transformation are infinitesimal, okay? This displacement are very slow, occur to a very small extent for a very small time frame, okay? All these things these experiments are thought experiments, okay, done in this following manner, okay? So involving infinitesimal displacement. Why do you do that, okay? It is important to understand that whenever we are trying to do this displacement, these intensive properties like pressure, surface tension, all these things, okay, this again, magnetic fields, electric fields have to be well defined, okay? So within the medium, there should not be differences in pressure. Okay? When there is a piston work, when we are talking about piston work, when there is displacement, there should be homogeneity in terms of pressure. Okay? When there is no homogeneity in terms of pressure, there can be flows associated with that. These are not reversible systems, these are irreversible systems. We cannot, within the framework which we are using, there is no way to incorporate such changes, okay? So these infinitesimal changes, we are emphasizing these infinitesimal changes so that these are well defined. These quantities which are indicated in the red, okay, are well defined during these transformations, okay? Then there is another, we could have called it quasi-static, okay? So that's also an equivalent, but there is another reason why you use this reversible transformation. For example, you consider the system, okay? So system changes. By a series of changes, the system is brought back to the same state, okay? So these are called cyclical changes, okay? So this is very important. We'll go into Carnot system and so on. These cyclical changes are very important for practical applications in terms of engines as well as formal analysis, okay? They have conceptual utility as well as practical utility, okay? By they, I'm referring to cyclical transformations, okay? So when we are thinking about cyclical transformation for the system, when the system is undergoing a change, the surrounding is also undergoing some changes, okay? So when the system is brought back to the original state, thermodynamic state, that's what you mean by cyclical transformation. For reversible transformation, the surrounding should also come to the same state, okay? So there should not be any change in the surrounding, okay? Both in terms of, intensive, extensive quantities, okay? So this kind of thought experiment is called reversible transformation. That is the second way of defining what's a reversible transformation. The first is infinitesimal these things that are indicated RGB, okay, are three different aspects. We first talked about infinitesimal. Now we are talking about reversible transformation. So in a cyclical transformation, both the system and the surrounding should come back to the same state. The third way is of elaborating what's a reversible transformation. All this during the transformation, all states are associated with thermodynamic state that can be indicated in the state diagram. We looked at state diagram, right? TV diagram, PV diagram. Okay, V refers to, let's say, intensive volume. Okay, okay, or can be extensive volume too. Okay, so that is volume divided per specific volume or the extensive variable volume. Okay, all these things are state diagram, right? So when there is a transformation, for example, in a PV diagram, during any point of the transformation, that all these, when we indicate the transformation by a line, okay, these lines are made up of infinite number of points. During this transformation, each of these points is a point that is a point in the state diagram, which is indicative of a thermodynamic state. Okay, so it is a well-defined thermodynamic equilibrium state. Okay, so this is the notion you have to get used to. Okay, this is a great jump in some ways, right? Whenever we are thinking about transformation, we have this notion of things not being in equilibrium. Okay, but for within this framework which we are using, we are going to use this notion of quasi-equilibrium states to talk about transformation. Okay, this is a big conceptual leap, but that is very powerful. Okay, that is very powerful for indicating bounds. Okay, in certain quantities. We'll talk about this more in the few lectures. Okay, so this is going to help us give you bounds and efficiency within the context of first law and also in the context of second law. Okay, so these quasi-static reversible transformation are very important. Okay, there are a lot of nuances associated with this, but just to get a closure, we have indicated three aspects. Okay, this aspect, this aspect, and this aspect. Okay, so within this, most of the notions of reversible transformations have been covered. Okay, so I'll stop here. There is one more aspect on exact differential and inexact differential with respect to work, and how do you quantify work in different contexts. For example, adiabatic, isothermal, isobaric, all these things have to be dealt with mathematically. So these two aspects have to be taken at least in this context of PV work. Okay, so we won't have time to go into these kinds of work in this introductory course, but at least you should be informed that such procedures do exist. But we will focus a lot on PV work and do some more work, okay, to quantify PV work in much greater detail. So with that, I'll stop this lecture. Thank you.